All right, let's talk about one of the most important things you need to know to build seriously fast apps, database indexing. If you've ever found yourself wondering how a database query goes from being painfully, agonizingly slow to basically instant, well, you're in exactly the right place. So, to really wrap our heads around why indexing is such a game changer, we first have to talk about the huge, massive problem that it was invented to solve. I mean, we've all been there, haven't we? Just staring at that little loading spinner, waiting and waiting for an app to pull up some data. A lot of the time, that delay comes down to a really simple thing: how the database is actually looking for your information. Without the right setup, it's a shockingly inefficient process. To put a number on it, just imagine you've got a user table with 100 million people in it. In a worst-case scenario, with no index, finding just one of those users could take up to 100 seconds. 100 seconds! Now, okay, databases have some clever tricks to bring that down, maybe to 3 to 5 seconds, but let's be real. Even 5 seconds is an absolute eternity when you're waiting on an app. So what on earth is the database doing all that time? It's doing something called a full table scan. See, your data is stored in these little 8K byte chunks called pages. To find one single piece of information, the database has to pull the first page into its memory, read every single row on that page, and if it doesn't find what it's looking for, it just throws that page away and grabs the next one. And it does this over and over and over again, potentially across 1 million different pages. It is literally like being told to find one specific sentence in a novel by reading the entire book word for word from page 1. It's just brutal. So how do we avoid reading the whole book every single time? Well, just like a real book, we use an index. Let's introduce the hero of today's story. A database index is, for all intents and purposes, a map for your data. Instead of wandering around every single street in a city hoping to find an address, you just look it up on a map and go straight there. The index is a totally separate data structure that just holds a value and a pointer, telling the database, hey, the data you want, it's on page number 753,421. So instead of scanning 1 million pages, you just jump straight to the right one. The difference is night and day. Okay, so when you create an index, what kind of map are you actually building? Well, the most common one by far, the one you'll find as the default in pretty much every relational database out there, is called the B tree. Now, if you've ever taken a computer science or data structures class, this should look pretty familiar. A B tree is just a way of organizing data into a sorted branching structure. You can think of each node in the tree as a little set of signposts, where each signpost points you down the right path to find exactly what you're looking for. It's just a fantastically efficient way to navigate these huge, huge data sets. And this right here shows you the B tree's 2 main superpowers. First, for an exact match, like finding a user who is exactly 51 years old, the database just follows a single direct path straight down the tree to the answer. It's incredibly fast. But it's also amazing for range queries, like finding all users who are older than 50. In that case, it just finds the starting point, age 51, and then efficiently scans across the leaves of the tree to get everything else it needs. This incredible versatility is exactly why it's the default choice for most things. But, and this is a big but, the B tree is not a silver bullet. There are some specific types of data, some specific kinds of searches, where this trusty structure just completely gets lost and becomes super inefficient. So let's explore where our hero starts to struggle. The 2 biggest challenges for a standard B tree are geospatial data and full text search. Think about it. How would you find all your friends within a 1-mile radius? Or search for a business that has the word pizza somewhere, not at the beginning, but anywhere in its name? These aren't simple, one-dimensional lookups, and that's where the B tree really starts to fall apart. Here's why the location thing is so hard. Geospatial data has 2 dimensions, right? Latitude and longitude. But a B tree can only handle 1 dimension at a time. So you could make one index for latitude and another one for longitude. But then, to find locations in a square area, you'd have to ask the database for a long strip of all the right latitudes and another long strip of all the right longitudes. Then you'd have to pull both of those massive lists into memory and do this really expensive calculation to figure out where they overlap. It works, I guess, but it is so incredibly wasteful. And the text search problem is pretty similar. Because a B tree is sorted alphabetically, it's amazing if you're searching from the beginning of a word, a prefix search they call it. Looking for business names that start with pizza is a piece of cake. But if you want to find pizza anywhere in the name, well, that alphabetical sorting is totally useless. The database has no choice but to just give up and go back to that dreaded full table scan we talked about in the beginning. So for these special cases, our general purpose B tree just isn't going to cut it. It is time to call in the specialists. For geospatial data, we've got a few really clever solutions. Geohashing is a super popular trick. It's this brilliant algorithm that takes a 2D coordinate and turns it into a single text string. And the magic part is, places that are physically close to each other end up with very similar strings. Then you can just build a normal B tree on those strings. So clever. There are also things like quad trees and R trees, which are true tree structures that group nearby locations into bounding boxes. You'll find R trees being used in big-time production systems like Postgres for Postgres. And what about for full-text search? Well, the answer there is something called an inverted index. It's a simple idea that completely flips the problem on its head. Instead of mapping a document to the words inside it, it maps every single word, or token, to a list of all the documents where that word appears. And look how simple it is in practice. If you want to find every single document that contains the word fast, you don't have to scan anything. You just look up fast in your inverted index, and boom, it instantly tells you check out document 1 and document 2. That's it. It's an unbelievably powerful idea, and it is the core technology that powers absolutely massive search engines like Elasticsearch. Okay, that was a lot, I know. We've covered a ton of ground. So let's wrap all this up and turn this knowledge into a super simple, actionable guide that you can actually use. When you're designing a system and you're thinking about how to make it fast, it really all boils down to this one simple question. The type of data you have and the type of questions you're asking about it will tell you exactly what kind of index you need. And here it is, your decision tree. It's this simple. Are you searching inside text data? You need an inverted index. Are you querying location data to find things that are nearby? You need a geospatial index. For pretty much everything else, exact matches on user IDs, range queries on dates or numbers, your default, your go-to, your workhorse tool is the good old B tree. And that's really the key takeaway from all of this. You don't need to go memorize the internal workings of an R tree. What's most important is that you develop that sixth sense, that gut feeling, for recognizing when a query might be inefficient. And just knowing that there's probably a special index out there designed to solve that exact problem. Which leaves us with one final thing to think about. As our data gets more and more complex, we're talking vectors for AI embeddings, multidimensional scientific data. What new indexing challenges are just around the corner? And what brilliant new data structures are we going to invent to solve them? Thanks for tuning in.